Hello. Uh, Good morning, students. So today we have new chapter, electric potential and capacitors. I will start electric potential and capacitors. This second chapter in the electrostatics, and previously we have studied about the electric field, Coulomb's law, other things you have already studied. In this chapter, we will study about the electric potential difference, electric potential energy, other things related to that. Then we go to the capacitors. So now, before starting this electrostatics chapter is relevant or is almost analogous to the first year chapter called gravitation, which you have already studied. Gravitation you have studied. So little bit concept, most of the concepts are related. Related means in the sense they are same. They are same. Electrostatics concepts and gravitation concept. For example, Newton's law of gravitation you have studied. That is force between the two masses, that is F is equal to G m1 em2 divided by r square. So similarly, Coulomb's law, that is force between the two charges, can be written as K q1 q2 divided by r square. So masses are replaced by charge. Masses are replaced by charge, and gravitational constant is replaced by electrostatic constant. So now here these are the things, basic things. So now first when studying about the gravitation, you have come across or you have defined the concept of potential. There you have defined the concept of potential. This potential, that is gravitational potential, you have defined. So that gravitational potential analogous to that gravitational potential, there is a electric potential with respect to charge. That gravitational potential is with respect to mass, or that is defined with respect to mass, and this electric potential we define with respect to charge. So just for understanding, I will just recall the gravitational potential, or just so potential energy, or just we shall study gravitational potential energy. Okay, so we know that when an object is on the ground, and this object is lifted up by doing an external work. By doing an external work, we can lift the object to a certain height h. When it is lifted to a certain height h, then a potential energy is stored in this object. That potential energy is nothing but work done in lifting the object from ground to this height. The work done in lifting the object from ground to this height, that work done is stored as the gravitational potential energy. So for this work done, we have to apply an external force. In the direction, in this direction, we have to apply an external force. Then only the object will move upward, and this external force applied is equal and opposite to the gravitational force, which is downward. That is nothing but the weight of the object. Gravitational force is nothing but the weight of the object, which is downward. So now, when this external force is removed, once the object is here, it will have the gravitational potential energy, right? Or it will have the potential energy. So now, when this external force is removed, or this work done is removed, then the object will falls down. That is, when the force is removed, the object will falls down. That means the potential energy is converted into kinetic energy. As the object falls down, the object will get the velocity, and it will moves downward. That means it is gaining the kinetic energy at the loss of potential energy. And the sum of kinetic energy and potential energy will remain constant. That is total energy conserved. Total energy is conserved. That we have studied in the first year only. We have studied. We have proved total energy for a freely falling body is constant. That is energy is conserved. So whenever the energy is conserved, that is the energy is conserved. So only the kinetic energy is the potential energy is converted into kinetic energy, or vice versa. So like that. Similarly, like that. In the same way, now I will define the concept of electric potential energy. Electric potential energy. I will define the concept of electric potential energy. So now let us consider a charge, a source charge plus Q. A charge is there at a point O. The charge is plus Q. And due to this charge, there will be electric field around that charge. There will be electric field around that charge that you have studied in the first chapter. Electric field. That is electric field intensity. So there is an electric field vector E. In this region, due to the source charge plus Q. And now a test charge Q0. A test charge Q0 is there, and this test charge Q0 is moved from the point A to B. This test charge Q0 has to be moved from the point A to B. So to move from the point A to B, we have to apply an external force. Or just I'll tell the charge Q0 is at the point A. The charge Q0 is at the point A, and it is in the electric field of the source charge plus Q. So this charge will experience as the electrostatic force. That is Fe is equal to E into Q0. Fe is equal to E into Q0, or Q0 into E. That is E is electric field and Fe is the force experienced by the charge. And this force is in the direction of the electric field, or it is outward. It is also positive charge. Test charge is positive charge, and this is also positive charge. So repulsive force. So this force is outward. That means this force will that is force acting on the test charge Q0 due to the charge plus Q will move the test charge away from the source charge. But we want for this test charge to move towards the source charge, then we have to apply an external force. We have to apply an external force. That external force is equal and opposite to the electrostatic force. The external force applied is equal and opposite to the electrostatic force. And now, when an external force is applied, that is, work is done in moving the charge from A to B. The work is done in moving the charge from A to B. And that is, now I'll take a displacement of dr is there. Where is the charge A to B? Let us consider the displacement of dr is there between the charge A to B. Then work done by the external force. Work done by the external force in moving the test charge Q0 from A to B is given by work done from A to B. Alright, AB. Work done from A to B is equal to, that is, work done is equal to force into displacement, that is when the force is constant. Now here if you observe, the distance between the charges is changing. So it is not a constant force, so we can say it as, so it is a variable force. So work done for a variable force, that is given by integration of F dot dr. F dr. That is how we write, and that is work done by the external force. Work done by the external force. So integration F dr, and this is a from integration from A to B. If you take A to B like this, you can write. This is work done in moving the charge, test charge Q0 from A to B. And now F external, that is external force, is same as the electrostatic force, but it is in the opposite direction. And Fe is given by E into Q0. So we can write. So therefore you can write work done from A to B, work done in moving the test charge from A to B as integration of F external. Instead of that, you write it as E Q naught, that is minus with minus. So minus E Q naught dr. Write like this. So Q naught is taken outside. Q naught integration of vector E dot dr from A to B. So this is the work done. This is the work done in moving the test charge from A to B, and this work done is stored in the test charge. This is the work done in moving the test charge from A to B. This work done in moving the test charge is stored as the electric potential energy. Is stored as the electric potential energy. Listen to the sentence correctly. This is nothing but work done in moving the test charge from A to B in the electric field of the source charge plus Q. Right? So this work done is stored as the electric potential energy in the test charge at the point between the points A and B. That is electric potential energy difference between the points A and B. Similarly, like in the gravitation we have defined a mass is moved upward, a work has to be done, and that work done is stored as the potential energy. Similarly, same way here, work done to move the charge from A to B is stored as the electric potential energy. So this work done is same as the electric potential energy difference. So that is electric potential energy difference. I will write it as delta U. So delta U, that is electric potential energy difference, is equal to, that is UB minus UA, is same as work done in moving the charge, test charge from A to B. Delta U is nothing but electric potential energy difference between the points A and B, and it is same as work done in moving the test charge from A to B. That is delta U is equal to UB minus UA over W A to B or W A B, you can write. So that means delta U, or just simply delta U is equal to, so we have got this one, so that is minus Q naught integration of vector E dot dr from A to B. So this is the potential energy difference, that is electrostatic potential energy difference between the points A and B in the electric field. So how you will define this one? How you will define? It is nothing but simply you can make electric potential energy difference. Electric potential energy difference between the 2 points in an electric field is given by the, or is equal to the work done in moving the test charge from A to B. The work done in moving the test charge from A to B will gives the electrostatic potential difference between the points A and B in the electric field of the source charge plus Q. Did you got the idea? Did you understood? Once again, just simply I will just revise. Okay. See here, a test charge is there, Q naught at the point A. A source charge is there plus Q. Due to this source charge, there is a electric field. There is a electric field vector E, and our test charge is there at the point A, and now this test charge will experience a electrostatic force, that is Fe is equal to E into Q naught, and this force will tend to move the charge Q naught away from the source charge, but we want to move this test charge towards the source charge plus Q. So an external force has to be applied. And this external force applied is equal and opposite to the electrostatic force, so that the charge moves towards the source charge without acceleration. That point you have to remember, without acceleration. That is, the external force applied is in this direction and electrostatic force is in this direction. Net force acting on the charge will become 0. Net force acting on the charge will become 0. So the charge will move without acceleration. So remember that point. So this external force is applied and then work done in moving the displacement between A and B, let it is as dr. Then work done in moving the charge from A to B is given by WEB integration of F external into dr. It is from A to B. Okay. So now F external is same as minus Fe. So Fe is vector E into Q naught. So W, that is work done, is equal to, if you substitute these values, so minus E Q naught dr. So Q naught is a test charge and it will remain a constant. It is taken outside, minus Q naught integration of vector E dot dr from A to B. And this work done in moving the test charge from A to B is stored as the potential energy difference. Is stored as the electric potential energy difference of the electric potential energy difference in the test charge. Understood? So therefore, electric potential energy difference, that is delta U is equal to UB minus UA. UB is potential energy at the point B. UA is potential energy at the point A, is equal to, that is work done. So therefore, delta U is equal to minus Q naught integration vector E dot dr from A to B. This is just how we got the concept of electric potential energy difference. Now this is electric potential energy difference between the 2 points in the electric field, right? So now electric potential energy at a particular point, we want at any point, electric potential energy at a particular point, say this point. Generally I am telling electric potential energy at this point. Then at a particular point, then we have to consider that the source charge, the test charge, not source charge, the test charge is moved from infinity to the point, this one, to the point P. I will say this point as P. So if the test charge is moved from infinity to the point P, that is, infinity is nothing but the distance far away from the source charge. At that point, the Coulomb's force between the test charge and the source charge will be 0. So there is no Coulomb's force. So there is no electric field. Electric field at infinity. So that is 0. So therefore, so Coulomb's force will not be there. Electric field is not there. So from that point, from that infinite point, we have to bring the test charge to the point P. So now work done in moving the test charge from infinity to the point B. Instead of P, I will take it as B. Okay. From infinity, somewhere from infinity to the point B. So that is work done in moving the test charge from infinity to the point B. So that can be done as is equal to, that is UB minus U infinity. UB minus U infinity. UB is the potential energy at the point B, and U infinity is the potential energy at the point at the infinity. Potential energy at the infinity, and that is equal. That is you can write it as once again I will write here only. So that you can write it as minus Q naught, as by using this one, integration from A to where? From infinity to the point B. So vector E dot dr. You can write like this. Or else there is a potential energy at infinity is 0. The potential energy at infinity is 0. UB minus U infinity. Right. So now potential energy at infinity is 0 because there is no Coulomb's force, there is no electrostatic field. So potential energy at the infinity is taken as 0. So UB is equal to, that is potential energy at the point B. UB is equal to minus Q naught integration from infinity to B vector E dot dr. So this gives the potential energy of the test charge at the point B. This is the electrostatic potential energy of the test charge at the point B. This is the potential energy difference. Potential energy difference between A and B. Potential energy difference between the points A and B in the electric field. And this is the electrostatic potential energy at the point B. So like this, we will define the concept of electrostatic potential energy. So now, here we observe that this electrostatic potential energy this electrostatic potential energy depends, or it is numerically or directly proportional, or it is depends on the Q naught, that is test charge as well as electric field. The electrostatic potential energy depends upon the test charge as well as electric field. Both are together I am telling. Test charge as well as electric field. Now we want a quantity. We want a quantity which depends only on the electric field, or which depends only on the source charge, not on the test charge. Then we define another quantity, that is electrostatic potential energy per unit charge, or work done in moving the charge, work done in moving the test charge per unit charge, work done in moving the test charge per unit charge, and that concept we called as electric potential. That concept we called as electric potential. Why we are defining this electric potential? This potential difference energy, it is electric potential energy difference or electric potential energy depends on Q naught and E. We want a quantity which completely depends only on the electric field or only on the charge plus Q. Then we define another quantity by doing this Q naught. So Q naught can be removed by taking a work done per unit charge, work done per unit charge, or work ratio of work done to the charge. So that quantity we call it as electric potential. Electric potential. So now I will tell about the electric potential. See here some points you have to remember here. Remember that in this whatever we have considered, some note points in this electric potential energy. So in this the work done, that is external work done, that is nothing but the work done by the electric force, work done by the electric force, because external force is equal and opposite to the electric force. That work done does not depend upon the path followed. That work done does not depend upon the path followed. That means we have taken from A to B directly. Okay, if you take the A to B path like this, then also the work done in moving the charge from A to B will come out to be same, because electrostatic force is conservative. Because electrostatic force is conservative, that we know. That like gravitational force is conservative force, electrostatic force is conservative. So work done in moving the charge from A to B does not depend upon the path followed. Does not depend upon the path followed. So whatever the path may be, so the work done will remain the same. Okay, that is one point you have to remember. And here next another point that you have to remember is the charge, the test charge moved from the point A to B such that it is moved without acceleration. That is, the acceleration is 0. That means the test charge is moved very slowly with a very small speed, with a very speed or constant speed we can tell. That is, the charge is moved from A to B with constant speed, very slow constant speed, or very slowly, or you can consider it as infinitesimally small values in terms of very small values. So that these 2 points you have to remember. Remember that work done in moving the charge from A to B in the electric field does not depend upon the path followed, and the charge is moved very slowly, that is without acceleration. That 2 points are very important that you have to remember. So you got the idea of electric potential. That is electric potential. Now I will talk about the concept of electric potential. Electric potential. So now simply just now I told electric potential, that is work done. Or first I will define electric potential difference. As I will tell electric potential difference. Electric potential difference. Electric potential difference, that is defined as the electric potential difference between the 2 points is defined as the ratio of work done in moving the charge from one point to another point against the electric field to the magnitude of the test charge. See here, I am defining it differently. You can tell many definitions are there. Electric potential difference between the points A and B. Electric potential difference between the points A and B is defined as the ratio of work done in moving the charge from one point to another point against the electric field to the magnitude of the test charge. That is electric potential difference. I'll write it as delta V. It is delta V is equal to work done in moving the charge from one point to another point, from A to B, to the ratio of work done from one point to another point in the electric field to the magnitude of the test charge. Test charge. Electric potential energy difference between 2 points in an electric field is defined as the ratio of work done in moving the test charge from one point to another point against the electric field to the magnitude of the test charge. Or another way you can tell this test charge which I am telling so far, it is nothing but a unit positive charge. If you tell it as a unit positive charge, this test charge is a unit positive charge, then we can define like this also. Instead of ratio, we can define like this also. Electric potential difference between the 2 points in an electric field. Electric potential difference between the 2 points in an electric field is defined as the work done in bringing the moving the unit positive charge. From one point to another point against the electric field. Understood? Another different way of definition. Definitions I am telling different. There is a electrostatic potential energy difference, electric potential difference between the 2 points in an electric field. Electric potential difference between the 2 points in an electric field is defined as the work done in moving the test charge, in moving a unit positive charge, not test charge, unit positive charge from one point to another point against the electric field of the source charge, So like this also you can define the electric potential difference. So that is in general electric potential difference. That is called as potential difference. That is nothing but potential difference is equal to, that is work done from A to B divided by Q naught. So work done to move the charge from A to B. Work done to move the charge from A to B. Here we have work done to move the charge from A to B. So that you can write it as potential difference is equal to delta V is equal to, so minus Q naught integration vector E dot dr from A to B divided by Q. So Q naught cancel. So potential difference you can write it as, this is from external force. So this you can write it as potential difference is equal to integration of vector E dot dr from A to B. This is the potential difference between the 2 points A and B. Potential difference between the 2 points A and B. Or you can write another way. Some other way also you can write like this also. Today's potential difference delta V is equal to, it is work done, it is nothing but delta U divided by Q naught. Or another definition, you can write another definition, that is potential difference between the 2 points in an electric field is defined as the ratio of potential energy, electrostatic potential energy between the 2 points to the test charge, ratio of electric potential energy to the test charge, or potential energy per unit charge. That is the potential difference. So therefore delta V is equal to UB minus UA divided by Q naught. UB minus UA divided by Q naught. Like this also you can write. Understood? So this is electric potential difference. So now I will define the concept of electric potential. In the previously, while I am telling about electric potential energy, first I defined the electric potential energy difference. I defined the electric potential energy difference, this one, and then after that I defined the electric potential energy at a particular point. Electric potential energy at a point B. Similarly, first I am defining electric potential difference, not energy. This is electric potential difference, this is electric potential energy difference. Electric potential difference between the 2 points. Now, electric potential at a particular point. We want electric potential at a point B. We want electric potential at a point B, that is VB. So for this, the test charge is moved from infinity to the point B. The test charge is moved from infinity to the point B. So infinity means a point where the Coulomb's force between if the test charge is at infinity and there is no Coulomb's force, there is no electric field, so there is no potential energy. So now the test charge is moved from infinity to this point, then how much amount of work has to be done? Work done in moving the unit positive charge. Work done in moving the unit positive charge from infinity to the point B. That work done is stored as electric potential at the point B. Electric potential at the point B. Raise electric potential at the point B. Electric potential at the point B, another definition, is defined as the ratio of work done in moving a unit positive charge from infinity to the work done, not in unit positive charge, ratio of work done in moving the test charge from infinity to the point B. Electric potential at the point B is defined as the ratio of work done in moving the test charge from infinity to the B to the magnitude of the test charge. Ratio of work done to the magnitude of the test charge. So it is, or you can write VB is equal to, that is work done from infinity to the point B. Work done from infinity to the point B, that you can write, that is, you can write directly, I will write it as, so VB is equal to, shall I write directly? So VB is equal to, so you will get, UB minus UA divided, UA not UA, U infinity divided by Q naught. UB minus U infinity divided by Q naught. And U infinity, that is potential energy at the infinite distance, is 0. So therefore, VB is equal to UB divided by Q naught. Generally, just you can write UB we got here. So that is minus Q naught integration vector E dot dr from A to, not from A, from infinity to the point B to the Q naught. Now Q naught cancel, you will get so electric potential at the point B, EB is equal to, so there is this integration of E dot dr from infinity to the point B. So like this. Got the idea? Did you understood? This is potential difference. This is electric potential at the point B. Once again I will tell her electric potential at the point B. Electric potential at a point in the electric field. Electric potential at a point in the electric field is defined as the ratio of work done in moving a test charge from infinity to the that point to the magnitude of the test charge. Or else you can tell another way by using unit positive charge also. So this is electric potential at the point B, and this is potential difference between the points B and A, and this potential difference, or further you can write this potential difference as VB minus VA. VB minus VA. That is nothing but potential difference. EB minus VA. EB minus VA. It is minus integration of vector E dot dr from A to B. You understood? So here we have studied the concept of electrostatic potential energy. In the beginning, potential energy difference. Then electric potential energy at a point. Then we have defined the concept of electric potential difference. And then electric potential at a particular point. Okay. So now this electric potential or potential difference is scalar quantity. The electric potential or potential difference both are same. Only the difference is that the potential difference is defined for 2 points in the electric field, and the electric potential at that point is it is defined with respect to infinity. Actually, we define only electric potential difference. We assume this one electric potential. We get the idea from electric potential difference. Okay. So now. So that is electric potential at this point we have defined. Okay. So now this electric potential or electric potential difference both are scalar quantities. They are scalar quantities. You know scalar quantity having only magnitude, no direction. Okay. Electric potential difference or electric potentials are scalar quantities. Now, what are the dimensions or what are the dimensional formula or what is the unit? Just we shall see the dimensional formula and unit. So, electric potential in general, you can write the formula like this: potential difference is equal to work done divided by charge. Potential difference is equal to work done divided by charge. So potential difference is equal to work done divided by charge, that is V, delta V. Both are okay, no problem. Work done. Work done. The dimension. First, I will take dimensional formula. So dimensional formula of potential difference. So now dimensional formula of work done. Dimensional formula of work done is ml square t to the power minus 2. Ml square t to the power minus 2. So that is dimension of work done. And charge can be done as current into time. Current into time. That is current is ampere into time t. So you will get the dimensional formula of electric potential as ml square t to the power minus 3 t to the power minus 1. So this is the dimensional formula of electric potential or potential difference. Electric potential and potential difference both will have the same dimension and same unit. Both are same quantities. Only with respect to what we are defining. We are defining potential difference between the 2 points in the electric field and electric potential with infinity to the point. Understood? So dimensional formula both are the same. And the unit. So now talk about the unit. The unit of electric potential is that is same. This here only I will write the unit of work done. Unit of work done is joule and unit of charge is coulomb. So joule per coulomb. The unit of electric potential is joule per coulomb, and it is named as volt after the scientist name volt. So it is SI unit of electric potential is volt. SI unit of electric potential is volt or joule per coulomb. Joule per coulomb or volt. So now define 1 volt. Define unit volt. So now how to define this 1 volt? It is potential difference or electric potential difference between the 2 points is said to be 1 volt. Potential difference between the 2 points is said to be 1 volt if 1 joule of work is done. If 1 joule of work is done. How much joule? 1 joule of work is done in moving the 1 coulomb of charge. In moving the 1 coulomb of charge from one point to another point. This one I will write it as unit. That is 1 volt. 1 volt. That is electric potential difference between the 2 points is said to be 1 volt. Electric potential difference between the 2 points is said to be 1 volt if 1 joule of work is done. 1 joule of work is done in moving 1 coulomb of charge. In moving 1 coulomb of charge between the 2 points. So that is how we will define the 1 volt definition for 1 volt. Understood? Okay. So this is just understanding of the concept of potential energy and electric potential difference and electric potential. So far we have understood mainly we have understood two concepts, that is electric potential difference, that is potential difference and electric potential. Electric potential. So now let us find electric potential due to a charge, or point charge. How much the electric potential will be there? So simplified formula for a isolated point charge. So electric potential due to an isolated point charge. Isolated point charge means a state charge separated point charge. So that is now I am deriving. This is 5 marks question. 5 marks question. 5 marks question. Electric potential due to an isolated point charge. And it's important. Many times they are asked in the theory exam. Here I am only teaching whatever the concept or whatever the physics I am telling in this classes only for theory purpose, not for the NEET level or JW level, just for basic understanding, and this is for just freshers second year batch. Electric potential due to an isolated point charge. So they will ask the question like this: derive an expression for electric potential due to a point charge. Simply derive an expression for electric potential due to a point charge. So now let us consider a point charge, that is plus Q. Consider a point charge plus Q at the placed at the origin O, and it is placed at a point O. Let us consider a point charge plus Q, or this is a source charge at the point O. So now this source charge will give the electric field. There will be electric field all around that we have studied in the first chapter only. Electric field due to this source charge. So now we want to find the electric potential due to this charge at any point. We want to find the electric potential due to this source charge at any point. So let us consider a point P. At this point, at the point P is a point at a distance r from the source charge. Let P be a point at a distance r from the source charge. At this point, we have to find electric potential. Electric potential at this point due to the source charge plus Q. Understood? So for that is according to the definition. First I will tell the definition. Electric potential, just now we have defined. How we have defined? Electric potential in a point in an electric field. Electric potential in a point in an electric field is defined as the work done in moving a unit positive charge from infinity to the dead point against the electric field. That's how we have defined just now. So now we have to find work done in moving a test charge Q0 from infinity to the point P. Initially, let us take the test charge Q0 is at the point A. Let us take the test charge Q0 is at the point A, and A is at a distance x from the source charge. Consider that the test charge Q0 is inside the electric field initially. Later it will be brought from infinity to this point. We will get it. Q0 at the point A, and this Q0 is at a distance x from the charge, that is source charge plus Q. Q0 is test charge and plus capital Q, that is the source charge. And now there will be electrostatic force. There will be electrostatic force between these two. So that is electrostatic force Fe is equal to, let us write K Q into Q0 divided by x square. q into q naught divided by x square, or you will write it as 1 by 4 pi epsilon naught q naught divided by x square. So this is electrostatic force, and this test charge is also positive, and this is also positive. So electrostatic force will be acting in this direction. Okay. So let us consider that the test charge is moved through a small distance dx. Let us consider that the test charge is moved through a small distance dx by applying an external force. By applying an external force, the test charge is moved through a small distance dx by applying an external force. So then we get that is the work done in moving the test charge through a small distance. Work done in moving the test charge through a small distance, that is small amount of work done. Dx is a small distance, so small amount of work done in moving the test charge is given by dw. dw is equal to it is work done in moving the charge through a small distance. So that is dw is equal to f into dx. F into dx. Fe into dx. It is work done in moving a small distance. This is dw is small amount of work done in moving a small distance dx. So now total work done in moving the charge q naught. Total work done in moving the charge q naught from infinity to the point A, from infinity to the point B. From infinity to the point B, because we want electric potential at the point P. We want to find the electric potential at the point P. Total work done in moving the test charge from infinity to the point P can be obtained by integrating this. This one. That is total work done is equal to integration of dw from where to where? From infinity to the point P. That is define the limits. That is x is equal to, x is the limit, x is equal to infinity. At this point x is equal to infinity. At this point x is equal to r. This point x is equal to r. Integration of dw from x is equal to infinity to r. So that is integration from infinity to r fe dot dr. Fe dot dx. So there is so now the electrostatic force is in this direction, and the displacement is here. So you can also write this as, so also you can write cos of 180 degree. Why? Because the angle between the force and displacement is 180 degree. Or you can write here only cos of 180 degree as minus Fe dx. That is work done by the external force. You get cos of 180 degree. So you get work done, W is equal to minus integration from infinity to the r, and Fe, that Fe can be done as 1 by 4 pi epsilon naught into q naught divided by x square into dx. Cos of 180 degree is minus, and this minus here. Got that here? So now work done, W is equal to 1 by 4 pi epsilon naught q naught, all are constant, take this outside. This minus 1 by 4 pi epsilon naught q naught divided by 4 pi epsilon naught q naught divided by 4 pi epsilon naught integration of x raised to minus 2 dx from infinity to r. So now integration. So you people are fresh second year students. I think you might be knowing integration. Or if you don't know the integration, just I will tell integration of x to the power n with respect to dx. Just integration, if function is there, just I will tell integration of x to the power n with respect to dx is x to the power n plus 1 divided by n plus 1. This is how we will define integration, that we have used it in the first year also many times. Just I am revising it. So using that you can write W is equal to minus q naught by 4 pi epsilon naught. So it is after integration you will get x to the power minus 2 plus 1 divided by minus 2 plus 1 from infinity to minus 2 plus 1 is minus 1. This is also minus 1. So W is equal to minus q naught divided by 4 pi epsilon naught So you can write it as minus 1 by x. Directly I have written x to the power minus 1. This is minus 1. This is minus x to the power minus 1. So that is in the denominator 1 by x. From infinity to, now substitute the limits. Once you substitute the limits, w is equal to minus once you substitute the limits, you will get 1 by r, minus 1 by r, minus 1 by r, and minus minus cancel. So you get directly, right? So 1 by 4 pi epsilon naught q naught divided by r, q naught divided by r. So what we got, this one is, this is work done in moving the charge q naught, work done in moving the charge q naught from infinity to the point p, work done in moving the charge q naught from infinity to the point p. So now we want electric potential at the point p. We want electric potential at the point, and we know that electric potential at a point is defined as the ratio of work done in moving the test charge from infinity to the point p to the magnitude of the test charge. That is divided by q naught. Ratio of work done to the magnitude of the test charge. So therefore you get, I'll write here, right? B is equal to, so that's work done from infinity to the point P, this one only. So it is 1 by 4 pi epsilon naught q divided by r. Okay, q naught cancel. So this is the electric potential at the point P. Electric potential at the point P due to the source charge plus q. So from this formula, we understand that the electric potential is dependent on the source charge, not on the test charge. Is not defined. Test charge, with respect to that test charge only we are defining 1 by 4 pi epsilon q divided by r. R is the distance of the point P from the source charge, that is from the plus q. Got it here? So V is equal to 1 by 4 pi epsilon q divided by r. This is the expression for electric potential at the point P due to the source charge plus q. Okay. So what if this is electric potential comes out to be positive? Okay. If the source charge is negative, then electric potential will comes out to be negative. If the source charge is negative, electric potential will comes out to be negative. So from this formula, we understand that electric potential is inversely proportional to R. It is inversely proportional to distance. That means if the distance is same from the source charge, if the distance is same, the electric potential will remain same for the same source charge. It is at this point. The same way, if you draw the circle, so all these points are equidistant from the point O. These all the points are equidistant from the point O. The point O is the place where the plus Q charge is, plus capital Q, that is source charge is present. So that is electric potential at all these points is same. Electric potential at all these points is same. That is electric potential is spherical symmetry. Electric potential is the nature of this electric potential is spherical symmetry for an isolated point charge. Understood the concept? Did you got the idea? Here, electric potential inversely proportional to distance and also directly proportional to source charge. Source charge is at the point O. So now the distance is kept constant, that is kept fixed. That means if you draw the points are different points, keeping the distance r as constant, you will get a circle. So it is spherical. So electric potential is spherically symmetric. Got that here? This is electric potential due to an isolated point charge. This once again I will repeat otherwise. Here what we have did is electric potential we wanted at the point P due to the source charge plus Q. What we have calculated, work done in moving the test charge from infinity to the point P. We have calculated work done in moving the source charge from infinity to the point P. Then divided by Q naught. Then we got the electric potential. At the point P. Understood? Got the idea? Okay. So this much is enough for today class. See, this is online class. Then this is first time I'm taking online class. So there are no students, only benches and all these things. So interacting class will be different. Naturally, when I take class in the students are there, it will be different, and here it will be little bit different. So if you did not understood, I will see this video. If I feel that you did not understood, I will remove some of the doubts which you might have during this class. Hello? ಆಯ್ತು ಕ್ಲಾಸ್ ಇಲ್ಲ ಅದು ಆಫ್
ಅದು ರೆಡ್ ಬಟನ್ ಒಂದು
ಇದು ರೆಕಾರ್ಡಿಂಗ್ ಉಂಟಲ್ಲ